Welcome to What Is It About the Weather, a podcast where we explore the many ways that weather intertwines itself into our lives. I'm your host, Mark Jelenic. This week, when the weather is the same but different. Hope your weather week's going well. I'm having a little bit of, fall, spring, whatever you want to call it. Feels a little bit like fall, but I know it's spring out there. Kind of a windy, blustery, some storms blew through. Yeah, the storms felt springish, but the weather after it definitely felt like fall. Even the wind profile and everything. He kind of opened window today, and it just kind of had that crispness of fall. Even had some friends that had snow where they were, and I've seen lots of pictures with snow on flowers this week or budding trees, and that's how I know it's spring, because the flowers are there. Otherwise, I wouldn't think so. Any case, it's pleasant for me. Those storms that blew through, I mentioned, it's kind of perfect for me, right? And you've heard me mention these things before. I had a little bit of all the senses involved. Definitely had that smell of rain, that we've talked about in the past. And some thunderstorms. I was in another room and just heard the thunder. Saw a little bit of lightning. All those things. Good senses exposure for me weather-wise. So, of course, I'm happy with that. Now, I will warn you, trying again to get back into recording more of during a day, during the week, and we'll see if it holds up. This construction project near me, it's not that it's loud all the time, but usually when I sit down to record is when they seem to find time to make noise. Hoping it won't be too bad. We'll get through everything. Now, I don't know about you, but when you see a weather headline, do you click on it? When you see a weather headline, does it pique your interest? Of course, for me it does sometimes and not others, just depending on what it is. But sometimes I'm not real happy with the headlines. And I saw one this week about a hurricane, or more, let's just say a tropical cyclone in the Atlantic basin, and people going, but hurricane season doesn't start for 2 months. Well, hurricane was in the southern Atlantic, and it's a tricky thing, because while a lot of places you'll see it not referred to as the North Atlantic hurricane season, that's really what it is. That whole area where you kind of hear, and they've been tweaking the dates even on that of what the norm is. But that window's about north of the equator, not south, for two reasons. One, we don't have that many of them that happen between South America and Africa. We do. I mean, there's, I don't know, on record, you average one every year or two. I don't know what the exact numbers are. So they're not in the official Atlantic database, but realistically, you would expect that season to be different, just the way weather moves back and forth between the northern and southern hemisphere different times of year, right? So I was not real happy with the headline, but I guess I'll forgive them because it's not always clear. And to me, that's part of the problem, right? We've got to be more clear in how we tell these stories, because a headline like that makes people, it confuses it all the way around, because it makes it sound like something happened well outside the season, which is, we've discussed before, can happen anyways, even in the North Atlantic. But it also implies somehow that the zone being covered is different, and it just causes confusion. But not that big of a problem. We got bigger things to worry about, and good things too, right? Drones on Mars. Helicopter flew this week on Mars. That's kind of cool, because they really do have to think about the weather when they do those things. They have to think about atmospheric pressure, and that was one of the big design issues with the helicopter, right? Let's call it, more importantly, it's a drone. It wasn't exactly a quadcopter, but like we're used to seeing here in a variety of uses. But the air is much thinner, and helicopters even, on Earth don't like to go too high because they have a hard time creating lift. And so it had to be designed to handle that. But I have to imagine they have to think about the weather forecast, whether it's going to be not so much rain, but windy or not. Because that thing's not going to go up in wind and be happy. I don't know. Just food for thought. Maybe keep that in mind next time you watch that stuff, that there's a weather component to it. All right. Let's get to the main topic. Now, I don't want you to Google this, but as you can imagine, I did, which is things that we think are the same but are really different. And you can Google it and you'll see 39 things, 17 things, 14 things, whatever it might be. And the list quite often the same, right? What's the difference between a rabbit and a hare, or a toad and a frog, and all these things? They go on and on and on. And I even laughed because one of them had weather versus climate, right? But the reason I was looking for that's a little different because, like I said, when I wanted to talk about this week, it's a little more sciencey. But I kind of alluded to it in the last episode that I was going to get to it because every now and then I get these questions, right? And they're not necessarily right for the podcast. But when I get a group of them, sometimes it can make a good diversion because we do get in the science of weather a little bit, but without dwelling on it week in, week out. And I did one before of why did I get that weather, right? And we talked a little bit about the science of weather and why certain regions get certain types of weathers. And, you might live in a place that doesn't and why you might not experience or why it might be unusual, like a tropical cyclone in the South Atlantic. But I wanted to come up with some examples that might be good that we do experience all the time of where things seem similar on the surface, but that aren't. Or when you start experiencing them, they don't exactly turn out the way you expect them. Because that's really kind of what I wanted to get to today. And like I said, the Google thing, it didn't really uncover anything that I thought was going to be useful. There were one or two examples in there that could have been useful, but most of them were really things that, I don't care that there really is an opossum and a possum. Do you know that? Not relevant for this case. They don't look at all similar. The biscuits versus cookie, it just went on and on and on. Nonetheless, I went back into my brain and I started picking out some things that could kind of be that way. And one of them happened this week anyway, so it was a good kind of side note. It had entered my mind, but then someone actually brought it up as an example, like, real world. But let's hit one as an example. All right, packaged goods. And you think about all of the things. You go to the grocery store, and I know a lot of people don't do this anymore, and you pick up a can of, peaches or beans or whatever it is. And let's say that can is 8 ounces or 12 ounces or 500 milliliters, whatever it might be. And you get home, and you expect there to be a certain amount of the fruit or the vegetable or the legume or whatever it is in there, and you come to find it's not. And a long time ago, they would have had a more pronounced problem with this because there was less regulation around it. Now, it's a little trickier to do because specifically when it's a type of product that you expect to be kind of the same from brand to brand, maybe the quality is a little different, or maybe they add some seasoning that you want in there. But what you don't want is to end up with something that's not the same if you buy product A or product B fundamentally, right? And that's why you'll see more descriptive packaging about so much of fruit by weight, even within that product, or even other products where they can say that, that chicken breast that you're buying might have so much water in it by weight so that when you're cooking it, that it gets down to a certain size so that you can do some comparable calculations when you're trying to decide what to buy and if one price is better than the other. Right? So this idea of things looking the same on the outside but being completely different on the inside, there are ways to manage that or to handle that. But let's take something more fundamental that many of us use, right? Like paper towels. And this was the example that came up this week when someone asked me, were these the cheap paper towels that we bought? Yes. Yes, they were. But have you ever done that? You've gone and you pull off 2 paper towel sheets. And this is why Bounty did ads for years, the quicker picker-upper, right? And they had all sorts of commercials about why this one's better than that one and the technology behind it. Because looking at it, you couldn't tell the difference. It just looks like, 2 white sheets of paper. Maybe there's a little print on it or whatever. But one might do a heck of a lot better job at its purpose than others. Same can be said of toilet paper, whether it's soft or not, right? And if you're just looking at things, you may not know. It may not be obvious. And I'll give you a more nuanced example because I think it's relevant to what we're going to talk about from a weather standpoint. This will be the last one, and then we'll get into the weather examples I wanted to bring up. interest rate calculations. Now, you may be aware of this and you may not. You may have never thought about it, but how much interest you either earn or pay, even when the two numbers from two banks are showing you the same, can be very different. And again, this is something that's become more regulated to try to make it more transparent. Because as an example, if you go and you compound, which is do the calculation, say you want to earn 1%, and I go and calculate it every day, well, I'm calculating that 1% on the new value, right? If I say this is 1%, even if it's earned over the course of a period of time, how often you do that calculation is going to adjust how much you earn or owe, and therefore effectively earn. And that's why they have APY versus APR. And I'm not going to get into all that, but that's why you have to pay attention to both of those to understand why Bank A and Bank B may be saying one thing and giving you something else, depending on how they go about the calculations. So you can see every day in life, we experience things that on the surface might seem the same, but when you dig a little bit, they're not. All right. And I wanted to bring up 3 weather examples that people have asked me about and kind of talk about them a little bit. So the first of these is atmospheric pressure. Now, we've talked about this recently, right? Talked about it in the cooking episode. Talked about it with my watch, remember? And why it's tricky. We have these devices that measure atmospheric pressure, right? And they've evolved over hundreds of years, maybe even longer than that. Different chemicals we use, different technology we use. Fundamentally, the idea is the same, which is looking up above us, how much does this column of air from the top of the atmosphere down to us weigh, right? Or how much pressure is it exerting on us? But when you look at the most common representation for seeing atmospheric pressure, it's often a weather map. That's where most people see it. Now, they may have heard a number in a weather forecast somewhere, and they may have paid attention to it, they may not. But the most obvious visual representation for most people is that weather map that has little lows and highs and maybe some other circles around those things. Well, those circles generally represent, they're not really exactly circles, but those lines that are drawn that seem to have some sort of pattern to them that go around the low and around the high. Those represent different levels of pressure. And again, depending on the map, it can be slightly different intervals. But nonetheless, the fundamental idea is to show you where the storms are, right? Or where the cold air is going to be coming from, or where the warm air is going to be flowing, that sort of thing. Very useful. And it's very useful in a way to help convey weather to a variety of people, different backgrounds, different understandings, but that you can quickly share some relevant information. Now, the problem with those maps is it's not actually what's read, right? It's not actually what the instrument kicked out. That is an adjustment. So when I say that my atmospheric pressure, wherever I'm at, which actually happens to be near sea level, which is relevant here, versus somebody standing on the top of Mount Everest, how do we equate the same thing? Well, we do this adjustment to create mean sea level pressure adjustments. The whole idea is we take a value at whatever elevation and we adjust it down the surface so we can get a sense of if we had, I hate to use the word flat Earth with no elevation or terrain, what the weather patterns would look like on that surface, right? And it's useful because generally speaking, even though things may adjust for elevation, I grew up, like I said, in Atlanta, and Atlanta actually has some elevation. Before, we started playing baseball in Denver, Colorado, as an example. It was, I believe at that point in time, it was the highest stadium above sea level and was well known for people being able to hit home runs. But the fundamental concept is trying to give a way to share weather data, because if we actually measured real pressure and gave you those numbers, it wouldn't make any sense. It'd be gobbledygook. And this gets back to the idea that as we go higher up in elevation, that column of air is not exerting as much pressure because the atmosphere effectively thins out and it creates less pressure going down. So the actual measurement is not the same. Although the real measurement that we use in these charts and these graphs, and the surface is not the only one where we get it. And mountains cause problems because even at some of the other layers, in theory, those layers are still above what the pressure reading is at certain elevations. And it can cause trickiness in weather forecasts. Mountains remain one of the harder areas to forecast because what may be an elevation, a map above a certain elevation, and makes sense when you're in low-lying areas, for telling you a little different about the weather behavior, might be in the side of a mountain somewhere else. So it's tricky. But it gives us a way to relate one to the other. So most of us never experience that number that's actually displayed. Even like where I am, I'm close to sea level, but if I go where I'm at in my apartment, the pressure's changed already, right? And so even the temperature can be slightly different based on that small increase in elevation that just goes up in my building. And so all these things we think about because this map somewhere shows this low pressure and high pressure and seems to indicate we're all in these little zones. The reality is once you start adjusting for elevation, it's not exactly the same. But it does give us that first order estimation of what we expect weather in point A and point B to be like, all things being equal as some, ground basic measurement system. So that's why it's that way. But it's also why meteorologists use it one way and pilots, as an example, don't. I'm going to put a link in the show notes that talk about the two different types of measurements because they need to know how high they are above the ground for when they're coming to land, right? I mean, that's particularly important. And so they're not interested so much in sea level pressure they might be interested in, but they need to think about it a different way because it's about how they adjust their instruments to make sure that they know the proper elevation, not to sea level, but above ground, all right? So let's take another. Humidity. And this is one I get asked. Actually, it's pretty common for me. And it's the whole idea of absolute versus relative humidity. Okay? Absolute humidity is just truly how much water vapor we have in an area of air. But relative humidity is a little different, and it's important, and it's probably the humidity measure you hear most often when somebody says it's 70% humidity or 80 or 20 or 40, or you hear someone trying to sell you a humidifier in your home, or you're measuring it, whatever it might be. And you've heard about me mention this in the cooking show as well, right? About how moisture makes a difference. But most of us have experienced this at some point in our life where we've stepped outside and it's felt muggy, maybe to us, it's really felt damp or humid. And I think relative's really an interesting term with humidity because many of us get used to different types of humidity profiles. And I think probably each of us have a range in which we're comfortable. And that may vary drastically from one person to the next based on where they grew up or how long they've lived in a certain area, right? Because there tends to be a sweet spot for most of us. Too dry, maybe your skin gets itchy or dries out easier. But too hot and, you start sweating and it doesn't evaporate. And that's really the idea of what's going on with relative humidity, okay? Because there is this pressure, but more importantly, a temperature component. And sometimes you'll hear a secondary number called dew point. And I'm not going to get diverted to that, but dew point is a temperature at which, if the temperature dropped to that, condensation would it's hence dew point. That's when dew would form. But you'll sometimes hear dew point referred to as being high or low, and that can be that comfortable factor, right? So if a dew point's really high, it actually means usually there's a lot of water in the air, but to get higher dew points, usually you have to have slightly higher temperatures. But maybe I've mentioned in the past, and I probably have, that once you get to, that's one of those things that I kind of watch as the marker from going from summer to fall is, in the South, it used to be when the dew point finally dropped below a certain value. You kind of knew that change was in because you could wake up, walk outside, and not feel like you were sweating the moment you walked out the door, right? But for somebody, and I've spent years in a dry climate as well, that got hot in Santiago, Chile, and it was very different. And this is the risk, and this is why you need to understand that In that climate, it got warm, but it never felt muggy. But at the same time, I probably had a real risk of dehydrating faster because I wasn't noticing the fact that I might be losing more moisture. Because really what relative humidity is about, we talk about air at a certain temperature holding a certain amount of water vapor, and it's not necessarily about how much it holds. It's about rates of condensation and evaporation. And what we do know is the warmer it gets, the easier it is to evaporate water. It makes it easier for water to be in a gas state in the atmosphere. Whereas the colder it gets, the easier it is to condense and take it out of the air. All right? So this is why it's important to understand where your temperature is relative to what that amount of moisture is. Okay? Because it's that balance that we're actually talking about. So we're discussing how much temperature or how much humidity is already in the air relative to the idea of what that balance is for that temperature. So there's actually an equation, a lot of equations. I was in a thermodynamics textbook this week, even looking at that stuff, being reminded of certain aspects. There's a whole chapter on, water temperature profiles and stuff. Just, this whole relationship between how we move from ice to solid, from solid to liquid to vapor and that sort of thing. So as you can imagine, it's not as simple sometimes as the equations. Again, I'll put a little link in the show notes that tries to explain it a little better and even brings up that dew point temperature. But it's important because it gives us a sense of what it really feels like. And this is why it's tricky. So if you get a number that says relative humidity 70%, well, that may not mean anything. A lot of times, I think it was shared in the past because it gave you a sense of maybe when it was going to start raining. But you can have rain and not be 100% humidity. Although 100% humidity is usually a good indicator of there being fog or mist or those sort of things if it's not raining. But it might give you a sense of how muggy it's going to feel if you know that 80% humidity with, 90 degrees Fahrenheit outside, it's going to feel a lot different than 80% humidity when it's 70 degrees. But how that humidity fits into the temperature profile, this whole real feel temperature that we've discussed before, gives us a sense of that, right? Because that real feel temperature, if it's really dry, you actually feel colder. And if it's really muggy, you actually feel hotter. And that's where it's become probably more useful and maybe why you don't hear it mentioned directly as much anymore. Because it's one of those variables that we tend to want to know how is it going to make us feel versus trying to understand what the actual value means. Right? So you can have 100% humidity, 70% humidity, but without the context of the temperature, that may or may not be meaningful. Okay? And it doesn't, it's not always a linear relationship. How 80% makes you feel at 80 degrees Fahrenheit or 35 degrees Celsius or 20 degrees Celsius. It doesn't, none of that, it gets down to being kind of individual. But that's why they have these charts and these ideas of kind of next stage analysis tools like a real field temperature. All right, let's talk about the last one that's a little more nuanced, but it's a little more basic. Relative humidity is calculated, right? And it is based on water vapor in the atmosphere. And atmospheric pressure, well, the one we use is adjusted. So those two things are kind of what I call adjustment calculations, but temperature is pretty basic, right? It's 50 degrees outside Fahrenheit, right? Or maybe it's 25 C or about 77 Fahrenheit. We'll put everybody in the same range. How does that feel, right? And how do you adjust to a forecast like that? And is the temperature alone enough? Well, probably not. And I had an example of this a couple weekends ago. Actually, or maybe even been last weekend. I was going for a hike. I was even asked, what's the temperature going to be like? It's going to be like this, but, I added, but it looks like it's going to be either mostly cloudy or overcast. Now, why does that matter? Well, it matters for a couple of reasons. One is it tells you a little bit about how much the temperature may change between now and when you're going to be doing a hike, which I was going to do, or how you might dress accordingly, kind of like real feel does with humidity, right? Because we sat down to eat a little lunch, and the first thing I heard was, "It's a little cold. I didn't expect it." And I started laughing. I said, "I mentioned it was going to be cloudy." "Oh, you didn't hear that part, did you?" "No, I didn't pay attention." It's more likely what the answer was. Because even something as simple as clouds impact the way temperature feels. And this is why it's funny. I have videos, right? Back in the early days of this podcast, I had a little series called You Ask, We Answer. But one of them I did was about weather stations, right? Personal weather stations, and going in and putting that little thing in the ground and why it matters, what it looks like, and what's called a radiation shield. Well, the radiation shield makes sure that that little temperature unit doesn't get direct radiation from the sun, because even sitting, and you've probably noticed this, and it varies whether it's sunny, cloudy, partly cloudy, mostly cloudy. When you're sitting down, let's say having some lunch, if the sun is actually on you, it's warming you up above what the relative temperature is around you. So that radiation is working on your skin directly. Makes you feel very different at 77 or 25 Fahrenheit, right? Or 25 Celsius. And it boils down to the fact that, the sun is warming the air around it, but it doesn't, the temperature is more of a mix of what the air feels like, not so much what it feels like on your skin. And when you get a lot of clouds, a lot of that radiation is being bounced back. And the reason it may feel 50 degrees is a combination of what the temperature is at the surface, as long as infrared radiation bouncing into the clouds and back to the surface of the earth, it all comes into play. But then you throw in humidity or wind. So even if there's no wind, and even if the humidity is identical, it's going to feel different based on whether the sun is directly reaching you or not. So it's nuanced. And how much that radiation can reach the earth during the day. I mean, it's an example. Clear days usually mean warmer, all things considering, because the sun can heat the earth and it can warm up. Whereas at night, you look for cloudy nights to keep it warm, because that infrared, that radiation escaping the earth is bouncing off the clouds and back towards the earth. It tends to keep it warmer. Maybe you've noticed that before. All little nuances, right? It's just a reminder that just like these little interest rates or paper towels, every day we deal with these things that at first glance look the same, but they're really not, for very subtle differences. And it's a reminder about how weather, just like life, is not as simple as that first glance. And just a reminder that there's much more to weather than the weather itself.